So next up, we do have Eric's presentation. What do geometric hallucination detection metrics actually measure? Right.
Great. Thank you for the introduction. I'm a scientist at PNNL. Today, I'll be presenting our work, What do geometric hallucination detection metrics actually measure? So we have quite a few co-authors on this work, and some of you might recognize some of them in the list. Before I continue with the rest of this presentation, I wanted to quickly define what geometric hallucination detection metrics are. And simply, they're quantities which are readily computable from the internals of LLMs that are known to be correlated with hallucination. So first, I'll provide a quick summary of the work, given that definition that we just gave. And we'll be designing a multi-domain data set simulating LLM hallucinations of various types and severities in order to answer the question, what do geometric hallucination detection metrics actually measure? Our first finding is that all geometric statistics are correlated with factual incorrectness or factual errors, but different geometric statistics respond to different types of misbehaviors. Our second finding is that domain shift impairs the performance of geometric statistics in hallucination detection in multi-domain settings. And we address this with a novel normalization technique, which yields 34 points or more increase in area under the receiver operating characteristic in detecting those hallucinations in multi-domain scenarios. So the motivation for this work builds off of how GenAI tools are rapidly being integrated into many other systems. And there's just a vast space of tasks that generative models can perform. And so this makes monitoring these tasks and monitoring them for misbehavior intrinsically challenging. So there are many different types of misbehaviors or failure modes. The broad one that we focus on in this work is termed hallucinations. And so hallucination can be an output that is factually incorrect or otherwise unsupported by the context given to the model. There are also other misbehaviors such as inappropriate use of external tools. So we have a silly example here. When we just first built the email agent, and one time we scraped the BBC News website and it failed. So it wrote an email to the chief executive of the BBC asking for permission to scrape the website. There's also a failure to follow instructions, which could have dire consequences. But then we also have inappropriate refusal. And another silly example here. So here we're chatting with Claude, and we ask Claude, how can I kill all Python processes in my Ubuntu server? Claude responds, I apologize. I should not provide recommendations about harming processes or systems. And then for one more example, you could have logic errors within reasoning chains. And so given this large array of types of misbehaviors that models can have, we ask the question, like, how can we monitor generative AI in a flexible and scalable manner? All right. So what our group does is we look to the model internals of LLMs as predictive signals of model misbehavior. And so if we look on the left here, we can see a simple depiction of two layers of a standard architecture for a large language model. We have MLP modules as well as multi-head softmax attention modules. And from different points in this network, we can gather, say, the attention maps of this model. So we gather those from the multi-head softmax attention. We can gather token representations, which are high-dimensional vectors, or the embeddings of the model. We gather those from the residual stream. We could also consider the output logits of the model in our analysis. And so each of these signals is not immediately interpretable on its own, but we can use machine learning or mathematical frameworks in order to interpret them and derive useful signals from them. So before I get into the main part of the talk, I just wanted to demonstrate with an example of how useful these model internals can be in predicting model misbehaviors. So here we have evaluated, and I'm not sure, it looks like some of my slide could have been cut off, but should be okay. We see that we've evaluated 15 models on Berkeley function calling leaderboard, and we gathered their hidden states for when they correctly call the tool versus when they have incorrect value errors. So in this case, an incorrect value error would be if the model got everything correct except for the exact value that it should have plugged into a tool. So this can be a very subtle form of error that is difficult to detect. Yeah, this is good. Thank you. And that subtle form of error is difficult to detect via traditional means, such as with code or with other models. And so we trained a simple linear probe on these hidden states or these hidden representations that we gathered from the model, and trained it to separate correct tool calls versus these subtle incorrect value tool calls. And what we find, as measured by the test area under the receiver operating characteristic of detecting these errors, we get very high detection scores, up to over 90%. And then the best score would have been Llama 3.370B, which was on the bottom of this table, but it's also over 90 in this case. So you can see that even these very simple small probes can get quite good prediction accuracy for these in this setting. So these are useful signals for us. Now, a limitation of the previous approach where we trained this linear probe is that we have to collect these hidden states in advance. We have to label the hidden states for a specific behavior that we're trying to detect, and then train this probe for detection. Now, in order to circumvent a lot of those steps, the field has found geometric hallucination detection metrics, which are these readily computable quantities from the hidden states and attention maps of LLMs, which are known to be, these quantities are known to be correlated with hallucinations. And so the first one that I'll talk about is hidden score, which is computed from the Graham matrix of the hidden state sequence. And so what it's looking at is the log determinant of this Graham matrix of the hidden states, and intuitively it's measuring how diffuse are the hidden state representations, where more diffuse hidden state representations are associated or correlated with hallucinations. The second that we consider is matrix entropy, and this is measuring the entropy of the eigenspectrum of the hidden states Graham matrix, where higher entropy is associated with hallucinations. Lastly, we consider attention score, which is computed from the attention maps. And these attention maps are lower triangular. We can very easily compute the log determinant of these attention maps, and this quantity is also found to be correlated with hallucination. Intuitively, what this attention score is measuring is how much do tokens attend to themselves. So the field had found that these quantities are correlated with hallucinations, but we wanted to dig deeper and find out if different metrics are correlated with different aspects of hallucination. Are there specific forms of hallucination that these metrics are effective for? And so the first step to answering that question, our first step was to curate a prompt response pair data set, which has objective and unambiguous answers. So we start out with correct prompt and response pairs from 3 domains. So we have what we call math, history, and counting, and note that they all have unambiguous integer answers. For math, it's multiplication questions. History, it's the year in which a famous event has occurred. And then counting is just how many times a string appears within a longer sequence. Now, we have these baseline correct prompt response pairs. We can simulate incorrectness hallucinations by just adding a numerical offset to this responded answer. So now 20 times 30, we simulate a factual incorrectness hallucination by adding 7 in that case. We can do similar things for history and counting. I'll note that we can control the severity of the hallucination, in this case, by adding an offset with a larger magnitude. But we don't have to just stop there. There are many other forms or ways to think about hallucinations. So we just talked about incorrectness. If we start from this baseline prompt and response pair, we can add verbal modifiers in front of the responded numerical answer in order to simulate underconfidence. We can simulate irrelevance by sampling a prompt question, which is different from the one that is addressed in the response. We can simulate incoherence by providing multiple numerical answers which are conflicting to the same response. And we can simply simulate incompleteness by truncating the response. And in the paper, we also provide methods to control the severity of these hallucinations, but I refer you to the paper if you're interested. Okay, so I just discussed this program to generate synthetic prompt response pairs. We have, correct prompts and responses. We have incorrectness. We have underconfidence prompt responses, things like that. And we can put these through the model and use a technique often called teacher forcing in order to collect the LLM representations, so these hidden states and attention patterns, which correspond to these specific prompt and response pairs. If you're familiar with the field and have worked with representation engineering, it's similar to that technique as well. So when we have these prompt response pairs, we've gathered the hidden states and the attention patterns from the prompt response pairs. We can compute our geometric statistics, or the hallucination detection metrics. That's the other way that we refer to them in this work. And I'll note that we conduct our main experiments using Llama 3.1 8B instruct. Okay, so here is a table of the test area under the receiver operating characteristic of each of those geometric statistics in detecting hallucinations of different types. So the decimal number that you see here, that is the ROC, or the area under the receiver operating characteristic, and then the number in parentheses is the layer at which that that metric was computed in the Llama model. As you look down columns, you can see these scores for the different geometric statistics on, say, math, history, or counting. And each column corresponds to a specific hallucination type, or in the case of incorrectness, a certain level of hallucination, where level 1 is the least severe hallucination, and level 3 is the most severe. So if we focus on this blue area in the chart, then we can see that more severe hallucinations, so going from level 1 to level 3, those are associated with stronger responses from the geometric statistics. Additionally, for these incorrectness hallucinations, we find that all geometric statistics are correlated with incorrectness. If we focus on purple, the purple part of the table, then we find that hidden score and attention score are good detectors for underconfidence and irrelevance. But for incoherence and incompleteness, which are in the orange part of the chart, we see that matrix entropy is a strong detector for incoherence, while hidden score and attention score are strong detectors for incompleteness. To sum everything up, we should look at the gray part of the chart. And so the gray part of the chart details the performance of these geometric statistics when we include a mix of the different domains for incompleteness, for incorrectness hallucinations. And what you can see is that the area under the receiver operating characteristic for these detectors, when there's a mix of all domains, this area under the receiver operating characteristic is much diminished. So we see that domain shift impairs the detection of incorrectness hallucinations on all domains. So we wanted to visualize this. And the x-axis of each of these charts is the layer at which, say, hidden score was computed, or in the case of the chart on the right, the layer at which attention score was computed. The orange lines on the plot are the distributions of, say, hidden score or attention score for history. The blue lines in the shaded areas are the distributions of the scores for math domain, and then we have counting in green. And so for both hidden score on the left and attention score on the right, you see that domain shift and its impact dominates the separation between correct versus incorrect responses on any given domain. So if we're going to use geometric statistics to detect hallucinations in the wild, where you might expect that there's a lot of variability in the domains that your detector needs to be effective for, then we're going to have to account for this impact of domain shift. So we developed this technique called perturbation normalization. We had found that geometric statistics are correlated with incorrectness, but they are strongly impacted by domain shift. So our idea to account for that is we want to compare the geometric statistic of the original response with that of nearby perturbed responses. And there are two cases that we need to consider. Let's consider if our original response is correct, then we'll look at the example. The answer to what is 4 times 3 is 12, right? We apply a perturbation distribution to the responded answer in this case, and then we get perturbed responses. The answer to what is 4 times 3 is 13, 9, 15, things like that. And in this case, we expect the geometric statistic of the original response to be lower on average than the geometric statistic on perturbed responses. On the flip side, let's say our original response was incorrect. So the answer to what is 4 times 3 is 11. We apply the same perturbation distribution, and we get our perturbed responses. In this case, we expect the score, the geometric statistic of this original response to be greater than or equal to the expected geometric statistic for the perturbed responses. Okay, so that's the intuition for perturbation normalization. And then now we can define it formally. So let's say we have our hidden states of the original response, and then we have, looks like it might be difficult to see here, but we have a collection of hidden states for the k perturbed responses. We also have a geometric statistic function, which which takes as input a sequence of hidden states and then outputs a real valued geometric statistic. We will then normalize this geometric statistic with the mean and standard deviation of the geometric statistics for the perturbed responses. So once we do that, we can see on the left is the original raw hidden scores, but then we apply perturbation normalization to each of those hidden scores. And we can see that the domains in this case align, where especially later on in the network, so on the right-hand side of the chart on the right, you can see that the scores on hallucinations are much better separated from those of correct responses, and they also align with those corresponding scores from other domains. And so the takeaway here is that perturbation normalization can reduce the impact of domain shift and enhance this within domain separability. So on the left here, we plotted the score distribution on all of the domains for the normalized perturbation normalized hidden score. And as the depth in terms of layers at which we measure the statistic increases, so we go right on that chart, we can see that we get much better separation between the hallucinations of various levels from the baseline correct response distribution. On the right, we quantify this with area under the receiver operating characteristic, and we can see that when we normalize hidden score, matrix entropy, or attention score using the previous method, perturbation normalization, and compare that with the best unnormalized performance on all domains, we get a much better detector score, an increase of up to 34 or more points in area under the receiver operating characteristic. So I'll summarize one more time. We designed a multi-domain data set simulating LM hallucinations of various types and severities to answer the question, what do geometric hallucination detection metrics actually measure? Our first finding was that all geometric statistics are correlated with factual errors, but different statistics respond to different types of other misbehaviors. Our second finding was that domain shift impairs the hallucination detection performance of the geometric statistics in multi-domain settings. And we addressed this with a novel normalization technique yielding 34 points or more ROC gains in our experiments. So here are the references for the work. And thanks so much for having me on. It was a pleasure to share this work today. So happy to take questions.
Excellent. Thank you, Eric. It was a pleasure listening to your presentation. We do have a couple questions ready to go. A question from Brian. Have you done any furthering of this research to see if the geometric shapes of confidently generated but factually incorrect information can be detected by distinguishing domain-specific signs of uncertainty throughout a confident shape?
Let's see. But factually incorrect information can be detected by distinguishing domain-specific signs of uncertainty through a confident shape. I think we had found in this work that there are a lot of aspects of, say, the domain or the way that you feed input into the model that could influence these hallucination detection scores. And so that's something that you have to consider, and something that's accounted for by this perturbation normalization technique. I don't believe that we looked too deeply into that specific scenario, but that's an interesting question.
Understood. Second question from Jide. Hello, Eric. Question is hallucination severity control a managing of the problem in your work? in parentheses, using geometric stats rather than correcting the issue, as opposed to a program that corrects the hallucination?
Yeah, that's a good question. So, I mean, for this work, we were defining what these hallucinations were, and once we could define the hallucinations and severity, we could measure the responses of these statistics and understand how these statistics behave a little bit better. I think that is an interesting question as well, though, where I don't know, you could have like a multi-step system that, say, could detect hallucination severity, and then perhaps you could employ methods to mitigate or like reduce the severity of the hallucinations and ultimately correct them. I think that could be interesting. Yeah, thank you. Thank you.
Understood. One final question for myself. I saw that this was a defined prompt and response for the given queries. I'm curious what we see as a conversation is prolonged with an LLM. Context or hallucination may drop significantly naturally. Is this something that was experimented on?
We for this work, we kept things much more granular and simple. I think it would get a lot more challenging with longer contexts, like those that a lot of LLMs are working with in their day to day. So the analysis could get a lot more complicated, say in just like tool calling, or if you're using LLMs for code or writing. So that's definitely a direction of future work, but another good question.
Awesome. Thank you very much. Um, Brian and Jonathan, thank you for your answer. Looking forward to following the research.
Thank you.